Howdy everyone, welcome back to the channel. Now I know what you're thinking. You're going to ask, is that a Hawaiian shirt with Godzilla on it? Why yes it is. Sometimes this is just how I roll. Anyway, it was a gift from my brother. So I used to wear Hawaiian shirts a long time ago. I haven't really worn one in a while, but you can't go wrong with Gojira. All right, so today's lecture is basically just going to be finishing up the lecture from last time on Venus and Venus, Mercury, and essentially the moon. And really what I'm getting into now is Mars. And I know that particularly given SpaceX's attempt at launching the Super Heavy, I know that Mars is sort of in the zeitgeist, and we want to put boots on Mars and all that kind of good stuff. So I thought I'd go a little bit more in depth with it. Now, like I said, it'll probably be a little bit short today because that's all I'm going to really going into. The end of the semester is approaching, and I am way behind. So I'm really going to push myself to put out a lecture a day. And I don't know when, but I will hopefully give you all more notice than now, or more notice in 10 minutes, what I'm going to give the next lecture. But anyway, let's get started with this. That one? How about that one? So what are we going to learn? Or what am I going to talk about? Basically, I'm going to talk about two things. One, why is Mars the way it is? And what is the geologic evidence that tells us that liquid water once flowed on the surface of Mars? Those two topics are somewhat interrelated in the sense that if Mars were physically different in one key aspect, then it would look a lot more Earth-like than it does now. Obviously, it would be different because it's a half again as far away from the sun as we are, but one key physical characteristic really prevented it from becoming, say, the second Earth. So I'm going to take myself out of the equation here. I think when I took myself off the screen, I think I'm. Yeah, so very early on, I took myself off the screen, and when I did so, I muted myself. So, as for me, I looked at YouTube, and you can hear me now. All right, well then, I'm going to start over. So, hold on. All right, so I think the last bit that people heard, because this is the slide where I took myself off, was this one. And what I was saying was that I have actually done a presentation that includes really kind of the whole story surrounding the canals on Mars business. In brief, where it started was with an Italian astronomer in the late 1800s by the name of Giovanni Schiaparelli. And what Schiaparelli did was he used a telescope, which was fairly large at the time, and observed Mars. And this was before photographic plates. So his map of Mars was hand-drawn. And among other features, he noticed dark lines, these linear features, which crisscross one another across the surface, superimposed on a much larger contrasting, lighter, darker areas. Well, he referred to them as canale. And in Italian, that strictly means channel. But when it was translated into English, it got translated into canal. And that led Percival Lowell to believe that these features were in fact intelligently designed and built. Lowell, through his observations, would later go on to add that this irrigation system, as he called it, would actually change with the seasons, that the Martians, for some reason, would dig their irrigation system and then dig it up and then replace it and so forth and so on. The best explanation, this is not real. These linear features are not real. We do not see them on Mars, as indicated by this really bad early photographic image of the Martian surface. I actually don't even know what the pedigree of that image is. If you obviously, we can find better, and I'm going to show you better. But what I'm saying is, you cannot, even with these earlier photographic plates, you can't see these features. The best explanation I've been given as to why they saw these features in the first place is apparently a psychological one. If a human being looks at an area that has some marked contrast across the surface and the image isn't very crisp, it's blurry, it's basically straining the limits of your angular resolution, then for some reason the brain wants to lie lines across your field of view. I don't know why. I don't know if that's true. I've never experienced it, but like I said, best explanation I've heard so far. Geologic processes that shape Mars, really what we're going to find is the same processes on Mars that we find on Venus, and to a certain extent we find on the Earth. The amazing thing to me about Mars is two things. Well, there are lots of many amazing things about Mars. The two that I'm going to highlight are that one, that Mars has two of the largest surface features on any other planet. And it is only the third largest terrestrial world. It is roughly half the size, the radius or diameter of the Earth, yet it has volcanoes and canyons which far outstrip or are far larger than anything we see on the Earth. So that there are areas on the Martian surface where there is a tremendous amount of geologic activity, a small localized area which we don't see anywhere else on any other planet, with the possible exception of Venus's resurfacing. Definitely not a small or not a localized area, I should put it out. The other thing that I thought that I'm going to talk about is the fact that Mars was this close, kind of potentially being the second Earth. There is one and really only one physical characteristic that dominated, or that really was deterministic in showing or in evolving Mars to what we see now, as opposed to evolving Mars into into something more Earth-like. So let's start off with cratering. We have on cratering, or on Mars, we see a variety of different craters. It is certainly more cratered than the Earth. It is potentially more cratered than Venus, but it is certainly less cratered than Mars, or than Mercury or the Moon. So it's somewhat intermediate, and there's going to be a reason for that I'll get into, why it's sort of intermediate. The other thing we see on Mars, very much like on the Moon, oddly enough, is that there are areas of enhanced cratering, or large. The population density of craters is large, and then there are areas where there are very few craters. That the landscape seems to be much smoother. That there are craters that seem to be absent. In order to have this dichotomy of heavily cratered regions and not so heavily cratered regions, you're going to have some mechanism via which those craters were destroyed. As I described in the previous lecture, that we went through an era of heavy bombardment. Every solid surface and every part of every solid surface inevitably got smashed into by some small to large-ish rock or block of ice. And so there was cratering everywhere. So in order for that cratering to no longer exist, something had to erase it, either erosion or volcanism. In the case of the Moon, we saw that it was volcanism. Basically, the crust broke open, lava upflowed onto the surface, and eradicated the previous cratering history. For Mars, it's a combination of that and something else. We definitely see volcanism on Mars. We do see a number of large of shield volcanoes. There are 4 in particular. If I were to go back to that slide, over here on the left, you might see under the dotted line, you see 3 volcanoes, shield volcanoes, kind of look like Orion's belt. That's known as the Tharsis Bulge, or rather, those are located on the Tharsis Bulge. And each of those would dwarf each of those would be far larger than any single mountain feature on the Earth. Olympus Mons, which is up and to the left, happens to be the largest volcano in the solar system. It is 21.2 kilometers in height, and in comparison, Mount Everest, depending on how you measure it, where your fiducial point is, it's around 9 kilometers in size. But regardless of how you measure it, Olympus Mons is roughly 2.5 times the height. In terms of area, as I am frequently fond of saying, it is the size of Arizona, or roughly the size of Arizona when plopped down on the United States. That's Mars's principal. Yeah. And then we come to Valles Marineris. There is, which is a canyon feature on Mars. And that canyon feature, again, is ginormous. If you were to place this on the Earth, it would span the continental United States. It would go from Los Angeles all the way to the eastern seaboard. Actually, if you tilt it right, it goes from basically LA all the way to New York City. It is it's not even worth comparing it to the Grand Canyon. But unlike the Grand Canyon, which is an erosionary feature, Valles Marineris is we believe to be a tectonic feature. Now, the reason why, one of the pieces of evidence which really got astronomers or planetary geologists to really think about something else, was that if you look at the ends of Valles Marineris, they have steep walls. There is nowhere in this feature where you can trace where water may have carved this thing out. So Mars, unlike any other world, with the possible exception of the resurfacing Venus, has undergone 2 major geologic pieces of activity on a very sort of localized scale. We do not see features like these anywhere else in the solar system. We do not see volcanoes that grow so large. We do not see canyon features that are so wide and so long. Yeah, Mars is a bit sensitive about things. I understand. I have a video which I'm going to see if I can pull up. It didn't get. It did not seem to get embedded with this. So let me, if you'll pardon me. There. I can find what I'm looking for. Venus. All right, Venus. There it is. Nope, that's not it. I don't care about making it better. Apparently it doesn't work on here either. Yay, LibreOffice. For LibreOffice for the win. All right. Oh. What I was going to show you was a very early simulation from JPL illustrating what it would look like if you did a fly-through of Valles Marineris. At this point, I will just find the video on YouTube, and I will link it into the chat, or I will put it in the description. It's a very cool video. It is from the late 90s, early 2000s, so it's very Tron-esque in its graphic capability. I'm sure at the time it needed a supercomputer in order to be created, but basically it's PlayStation 2 style graphics. We can do much better than that. So let's move on and talk about water on Mars. One of the reasons why Mars gets so much attention is because of the idea that Mars can be habitable or was once habitable, meaning that Mars had or has life on it. And so, people can get behind that. The public can be like, and can really get enthused, and their imaginations can run wild as to what kind of life may have existed and may still exist on Mars. Because one of the things that you need, assuming nothing weird happened or is out there, assuming there is no weird biology we haven't encountered yet, or chemistry that we haven't encountered yet, one of the things that you need for life to come about is a soluble surface or soluble substance. Specifically, in this case, water is the best example of it. However, it is possible, we at least believe that it might be possible for liquid methane or liquid ammonia to also be substituted. But that's really an open question. Definitely we know, because of the one data point we have here, that water is a great substance via which the material of life can get together, have a party, and get larger. So if we can find water on Mars, liquid water on Mars, then we have a pretty solid, well, I wouldn't say a pretty solid case for life existing, but we certainly now have opened the door for it to have existed. If we had found no water on Mars, like with Venus, then we can pretty much shut the door on the idea that Venus ever had life at any point. There is some pie in the sky idea that there might be living organisms in the upper cloud deck, but that's still very much specious at this point. Evidence is great. Anyway, water on Mars. What pieces of evidence do we have? Well, we have these surface features which show essentially what we're looking at. It's kind of hard to see with the contrast, but over on the left, you have this kind of darker region, and you have a couple more pimples on it, which are basically caldera or volcanic. Basically, you can think of them as uprisings of material from underlying volcanism that is punched up and basically lifted up the surface. We see evidence of this on the Earth, Venus, and I believe we also see it on the Moon. That dark area you can think of as dry land, whereas that lighter area that sort of snakes through the image, that is very reminiscent of riverbeds here on the Earth. That sort of pattern which gets marked out by rivers, very similar to what we see on Earth. Is this conclusive? No. It's simply one nail well, not in the coffin, but there's simply one building block upon which the evidence is built. We also see erosion of craters. So again, we have here, this is we have a lot of different craters on here. They're circular, but what we notice is that the crater rims are all very shallow. For the diameter of the crater, the crater walls are far too short. And so this would indicate to us that something, hey Roke, howdy, that something eroded those crater walls down to what we see now. Now, could it be wind? Possibly. But what we now know, but if what we know today is true, there is really very little atmosphere for a large wind, a forceful wind to be generated. Or is it rain? Well, that would make more sense. That would be more feasible, although if you have rain, you have a thicker atmosphere, so it kind of chicken egg. Current prevailing idea, though, it is that these erosionary features were caused primarily due to rain, rather than, say, wind action. In any case, there is obvious erosion going on here. Then we see, this is a computer-generated view in the sense that the colors are false color. They indicate different mineral species that were observed by a Martian orbiter. Yes. Aliens. Yes. I'm definitely, yes. But no, I would never say that the aliens exist. So with the, and also as noted in the caption, the topography is exaggerated 14 times to really illustrate that this feature is real, that this feature exists. What we're seeing here is analogous to a large lake next to feeding water out to a larger body of water, either a gulf or an ocean or what have you. Again, we see this on the Earth. And then finally, we also see evidences of river deltas. And in this case, it's really kind of evidence of flooding. So the idea here is on the left, you see that sort of riverbed-ish kind of feature. And then you see these two kind of mountain ranges type things with a valley in the middle of it. And then you see this river delta silt-looking feature on the right. So the idea is water from the river flowed in and probably slowly eroded it over a significant amount of time, and then a massive flood came in and broke through that wall and dumped out into the surface of the crater. Again, any single one of these is tantalizing. But when you put it all together, you really start building a strong case that water once flowed on the surface of Mars. Other pieces of evidence that we've seen is on the left, we see Endurance Crater taken by, I'm going to get this wrong, but I'm just going to go off on a wild guess and say, wasn't Perseverance. I'm going to go with Opportunity. It's probably Spirit, but anyway, one of the rovers, but that was not Pathfinder or Perseverance, took this image. And what you probably can't tell very well on this slide is that these sort of grayish little dots or areas on the bottom half of the image, those are round, those are spheroids of rock. We see, again, similar evidence of this in the Earth in Utah. And no, it's not because we shot that picture in Utah. It's because this particular type of geologic feature occurs when moisture is present. When there is moisture in the soil, then these particular types of rocks occur. I believe you need to have flowing water, but we're getting to the edge of my expertise. So I'm certainly not a planetary geologist. Another image taken by the by a Martian rover, presumably the same one in Endurance Crater. Again, we see this linear feature of rocks, which again, we see here on Earth, and the explanation for why they form this way on the Earth is because of water action over the rock. Finally, we have hydrogen content. Hydrogen, or water, as I hope you all know, is H2O, dihydrogen monoxide. And what we've done here is, again, this is, I think, the Martian Surveyor orbiter has done a spectroscopic study of the surface, specifically looking for hydrogen. So areas that are red indicate a very low presence of hydrogen, and then blue indicates a very high level of hydrogen. And you can see those are sort of localized. And in the bottom part of it, the bottom sort of pole, you have a very large area of blue, basically the entire pole at that point, which I think is the northern. I think this is flipped, although I can never be too sure. One of the poles is has a lot of hydrogen content on it, and then in the other hemisphere, we have a lot of hydrogen content, but not very much. The idea here is, or what the hypothesis that's being proposed is, that where the hydrogen content is located now was where oceans existed in the past. And so Mars did not have, if this is true, then Mars did have vast oceans, but not as large of oceans as we find here on the Earth. The surface area of the Earth is 71% covered in water, whereas with Mars, I think it's actually less than 50. It would have been less than 50. But there would have been large ocean features, assuming the hydrogen content here is telling us that is true. Hydrogen is there. It's just the hypothesis or the conclusion that we're drawing is that ocean water may have existed there. We see from crater walls, from closer in images taken by subsequent satellites, we see what appears to be mudslides. You have the crater wall, and then you have this sort of I can't think of another name for it, but a mudslide. The idea here is that this sort of feature, so all the other features that I was talking about before, required water being in a liquid state on the surface at some point in its geologic past. This is more than likely a newer feature. For this to occur, the hypothesis is that we are through other observations, we are very confident that there is a level or layer of frozen water just underneath the surface called permafrost. And we see evidence of this on the moon. Here, what we suspect happened is, and you can see it's on the lit side of the crater, is what we believe happened is that maybe over time this effect built up, or this particular part of the crater was thinner, the permafrost was closer to the surface. However it happened, what we believe is that one portion of the crater wall, the permafrost was substantial and close enough to the surface that the warmth of the Earth, or warmth of the sun, managed to penetrate through the surface soil and melt that permafrost for at least a short period of time. And that caused the overall surface above it to slide downward. So basically it greased, you can think of it as greasing the slide. Now it created a lot less friction for the upper layer of material to exist on that crater wall, and so it slid down as a mudslide. Mud flood. No, it's not quite a mud flood, but and again, this is just even more evidence from the Mars Express 2003, which I think was British. I could be wrong. Here, what we're seeing is, yet again, the idea is a massive flood. You have, from the left to the right, you had water streaming in, breaking through crater walls of surface features, and then dumping into potentially the vast ocean that is on one hemisphere. I really do think it's the northern. I think that map is flipped, or the Crissia Plantitia. And this, we believe, occurred 3.5 billion years ago, which is a common theme. So the common theme of this is that piece of evidence, that 3.5 billion years, comes up in other pieces of evidence in terms of water, and also in terms of the atmosphere. What we believe happened is that during its period, during its lifetime, Mars had a fairly substantial atmosphere. What that is composed of, I believe, is still an open question. We now know that Mars has a very tenuous atmosphere that is very much like Venus, is composed of carbon dioxide. And most of that is actually produced or contained within the poles. The poles are primarily dry ice. And so once one hemisphere experiences summer, the dry ice sublimates, carbon dioxide gets thrown into the atmosphere. As it goes into winter, the carbon dioxide freezes back down onto the pole. But we suspect that it had a much more substantial atmosphere, and we also suspect that atmosphere contained water vapor at some point. And so the atmosphere could have been very similar to the Earth, meaning that we had land masses, we had ocean water, we have rivers, all the little pieces of evidence that we've been showing before. And we had rainfalls and storms that created erosion on its surface, and so forth. But why is it that Mars now looks far less moist than the Earth does now? Why is it that Mars is essentially a desert planet, Arrakis? Looks like Arrakis. The reason for that is mass. What we suspect happened was that because of Jupiter's location in the solar system and its motion due to planetary migration, it, as I like to say, threw its weight around. And as Mars was forming, obviously, if you remember, Mars formed as the other terrestrial worlds did, or terrestrial planets did, through a process of accretion. Smaller objects slammed into each other, melted, fused together, and built up a larger object. With Mars, what we believe to have happened is that basically it ran out of material. It formed up to the Mars shape, and then Jupiter had knocked away all of the remaining material that could be used to build it up any larger. So without Jupiter being there, it's potentially possible that Mars could have been the size of Earth, or more comparable to the size of Earth. Who knows? Maybe even larger. Jupiter is a big planet, moves a lot of stuff. Because it has a very low, because it has low mass, it also, let me back that up a moment. It has a low mass, and it also has a low and a small radius. As I said, the radius of Mars is roughly at 1/2 of that of the Earth. The density is also lower. It's about 3.35, I think, as opposed to the 5.56 here on Earth. What that contributes is two major things. One, from a mass perspective, it could not hold on to its atmosphere. The reason why an atmosphere sticks around is because the thermal energy of that gas is insufficient to propel those gas molecules at a rate fast enough to escape out into space. Essentially, they're just too heavy. They just fly around the Earth. They're held in by gravity. They do not require a container, and they just fly around, but never with enough speed to fly out into space and be free and go out into the solar system. And gravity is mass dependent. It not only does depend on the mass of the planet, but it also depends on the mass of the particle. So the reason why Earth does not have, say, a thick hydrogen and helium envelope or atmosphere is because hydrogen and helium are the lightest elements, and they quickly, at least astronomically speaking, they quickly bled out into the solar system, and were replaced through volcanism with the atmosphere that we have today: nitrogen, oxygen, carbon dioxide, yada. Believe the same thing happened with Mars, that it once had a hydrogen helium envelope that got knocked away. That was replaced by volcanism, by some other atmosphere, possibly nitrogen, again, possibly very similar to that of the Earth, but certainly containing water vapor. And from that, water fell into the surface. But because of the lower mass, elements like oxygen, nitrogen, were able to actually have enough. Were actually able to have enough speed or thermal energy to fly out. They had the escape velocity necessary to leave Mars for good, ultimately leaving behind the very tenuous carbon dioxide atmosphere we see today. And we believe all of that happened. Really, the tipping point of it really happened about 1 billion years ago, is where we really stopped seeing evidence of active flowing liquid water on the surface. When we do see evidence of sort of flowing, like mud floods or what have you, really what we're seeing is these are younger features, and really, like I said, they are more than likely due to the underlying permafrost melting. Liquid water has never been is not on the surface of Mars not only because of the temperature, but mainly because of the pressure. Now, the other reason why Mars does not have a substantial atmosphere is, as I've mentioned, in order to gain the atmosphere that we do, or that we have, you need a lot of geologic activity to continually supply these heavier elements to the atmosphere. Even today, we are bleeding off gas. We are bleeding off atmosphere. But these are constantly being replenished by active volcanism. Now, with Mars is half the size. And again, going back to a previous lecture, I said that the timescale of cooling of a planet losing its heat, which is what drives volcanism and tectonics, is proportional to 1 over the radius of the world. So Mars cools twice as fast as the Earth does, simply because it's half the size. So again, we believe that significant volcanism, or significant geologic activity, ceased about 1 billion years ago. Now, I've heard some conflicting, I've heard some people claim that Mars is currently geologically dead. I have heard some say no, that there is some level of geologic activity that is still there, particularly the core. The core may still have a liquid or semi-fluid layer to it. But at this point, it's certainly not the Earth. It's certainly not having their Olympus Mons is dormant. It is not erupting. There hasn't been a volcanic eruption on Mars in recorded history, at the very least. Probably much longer than that. And there are no earthquakes and so forth and so on. So, and with that, I'd just like to say we have explored Mars quite a bit. And here, I don't think this is an exhaustive list, but it is really just a sampling to let you know that not only have the United States looked at Mars, but other countries as well. The Soviets, although as my old professors would like to joke, the Soviets weren't so good at actually hitting Mars. They sent a number of probes that completely missed the planet, and then a few more that did hit the planet, but hit it so hard that they blew up. But you can see here that there are some, I believe there are some Chinese probes, although that may be the Soviet Union. There's definitely a Japanese. The Europeans are in there. There's definitely the Brits have sent a couple. Mars has been well studied. I would hazard to guess that of all of the worlds in the solar system, It is the second most studied planet behind the Earth. And the reason why we study it is because of I would trace it all the way back to personal law. The idea that Mars could potentially not only have life on it, but support life. The idea that Mars can be another bastion of humanity. We can go there, we can develop it, we can cultivate the planet and actually live there as a second home. I think that idea is overhyped. There are certain challenges that I do not think are surmountable on any time scale in terms of terraforming Mars, primarily because it's too small. It's just too small for, I think, any kind of serious terraforming to exist on it. But that hasn't stopped us from exploring the hell out of it. The other thing that I think, honestly, is that it's easy. If you compare so our two closest planets are Mars and Venus. And as I mentioned, Venus is a hellscape. Getting a probe through the atmosphere onto the surface has only been done twice, and that has been the Soviets. We haven't been able to send a probe down there because I think, honestly, for what we know of it in terms of its cost benefit, it would be so costly to design and build a probe or a rover to actually survive on the surface of Venus than it would be to have, ooh-ah potential. Like on Mars, hey, Congress will give you the money because, hey, life, yay. Venus, not so much. We have no expectation that life on Venus could exist. So Mars, much easier to get to, and the whole life thing is a much larger driving factor in terms of funding. So am I suggesting that Musk is some sort of fantasist? No, I would never do that. I would outright state it. Musk is a fantasist. I would even go so far as to say that Musk is a functional idiot. But that's probably my own personal feelings getting involved. But no, Musk is definitely a fantasist in terms of what he expects to be able to accomplish in the next decade, keeping on topic with Mars and also in what he has said he wants to do with Mars once he gets there. So anyway. So yeah, like I said, that's it. I hope you found this educational and hopefully also a bit entertaining. And thank you all for being here. As I said in the very beginning, for those of you who may have missed it, I am very much behind in posting these lectures, so I am going to make a very concerted effort to start posting lectures every day until I finish off the outer planets and the sun. The sun will be the last thing I talk about in the solar system lecture series. So yeah, so that will be done in Earth for the win. Yes, Earth. Yes, Earth is what we got. It is the best. It is the best world that we have. It is really, I think, the only true home that humanity will have, at least for the foreseeable future, even in terms of geologic time. But that's a subject for a different time. I may, and I do mean may, be going live later tonight because I believe that we actually have a functional telescope again. It is a clear night, and I don't believe anyone has signed up to use the telescope, but I need to verify that. If that is the case, if all of that holds true, then maybe in a couple hours I will go live and I will just play around and let people watch. Granted, it will be close to midnight here in the U.S. on the Eastern Seaboard, but maybe there's some night owls out. All right, I believe that's it for now. Have a good one. Peace out. Clear skies, and I'll see you on the next go round.